Morning, we're going to look at tangency in a somewhat more general sense. So we begin with an objective function which is given by f of x. So what this implies is that the objective function is non-linear, and we assume that x is given by this column vector x1, x2, and then we assume a constraint g of x is equal to some value c, which is just a scalar or constant. For example, we could have thought of the budget constraint as being linear here. So g of x in this case would be linear, p1 times x1 plus p2 times x2. Notice, however, that I've switched from q to an x, and the reason is that the x is more general in this case. We don't want to keep it our discussion at the budget constraint maximizing utility. All right, now what we're going to do is look at what we've done in the previous lecture, and that is again looking at arbitrage, but then from a slightly different angle, and that angle is the fact that we're dealing with nonlinearities. So if we take the total derivative of d of x, or rather we just pick some small infinitesimal change in x, then that carries over in our notation to a change in x1 and a change in x2 given by that column vector. Now consider an infinitesimal change in the objective function f of x. Now we write that as follows, that the infinitesimal change in f of x in the objective function is given by the value of the objective function at x plus some small change, d of x, minus f of x. So that explains the change. And we write that as f1 of x, where f1 of x is simply this derivative down here, the partial derivative of the objective function with respect to x1 in this particular case. So the total derivative, the total change, this total infinitesimal change in the objective function can be written as the partial derivative of the objective function with respect to x1 times the infinitesimal change in x1 plus the partial derivative of the objective function with respect to x2 times an infinitesimally small change in x2. And what this really is, even though we haven't talked about it yet, is it's a first order linear Taylor series expansion of the objective function. Now assume a similar change occurring in the constraint set. All right, and we get the same expression, but now we've got a g of x instead of an f of x. So the small change in the constraint is given by the first derivative of the constraint with respect to x1 times d of x1 plus the small change in the derivative x2, the small change in x2 multiplied by the partial of x of g with respect to x2. And these are just explanatory, telling you that the subscript, in this case a j over here with the objective function and I, is simply equal to the partial of that particular function at an optimum, which we denote by x star. Then we have the small change in the objective function being equal to 0, and the same thing with the constraint. These small changes would be equal to 0 at the optimum. So then we can write that the partial of the constraint function with respect to x1, when evaluated at the optimum, has to equal to the negative of the partial of the constraint function at the optimum with respect to x2, and we set that equal to a common little change in the constraint right-hand side. So what we're doing basically is we're taking this equation here, all right, and setting it equal to 0, all right, set. So we set that equal to 0 down below, and we also assume that we get this little change here of the right-hand side of the function or the constraint over here. All right, given that, and don't worry about the negative sign at this point, okay? So from that, if we have that any one of these G1 evaluated at X star or G2 evaluated X star, if those are equal to 0, then what we have is that the dxj is equal to dc over that. So basically what we're doing is we're solving for dx1 and dx2, and we get this result here. Okay? Now don't worry about the negative sign as I mentioned. So now we're going to substitute this value here, which I've rewritten down here, in the equation for d of fx. So into this equation here. All right, we're going to substitute these values in there. And when we do that, what we do is we get this result. All right, that f1 over g1, both evaluated at the optimum, minus f2 over g2, both evaluated at the optimum. All of that multiplied by this d of c. Now, if the expression in brackets is non-zero, fx can be increased by choosing dc to have the same sign. If x star is optimum, the expression in brackets will equal 0. So if we're at an optimum, then this should equal 0. All right, in which case we get that these expressions are equal. Okay, so this is our condition here, which is similar to what we had in the previous lecture. All right, so we got the first derivative of the objective function with respect to x1 divided by the first derivative of the constraint with respect to x1 equal to that same ratio, the first derivative of the objective function with respect to x2 divided by the first derivative of the constraint divided by x2. And this is the arbitrage condition, which we'll discuss in greater detail a bit later on. So let lambda equal the value common to both sides of the above expression, in which case we get this result here. Okay, so this is our expression where the derivative of the objective function with respect to any one of the choice variables divided by the derivative of the constraint function with respect to that same choice variable is equal to lambda at the optimum, which is indicated by the stars. So if we solve that equation that I've circled in red, we get this result here. And lambda in this case is the rate at which the optimum value of the objective function responds to a change in c. Now that is a very important expression. Okay, this is very important expression, and we're going to come back to it quite a bit because that in effect is a shadow price, as we will see when we get to that point. Now, strange results occur when, for example, the price of one of the goods is 0. This is discussed in quite a bit of detail by the author Dixit on pages 13 and 14 of your text, but basically he's looking at what happens if we have a free good. Now we can look and see what a free good looks like, you'll notice that the demand function will cross the horizontal axes before supply occurs. So in other words, we have supply and demand effectively intersecting at a negative point, which is of course impossible, and therefore the price is equal to 0. So if we write a budget constraint in this case, where we have these two goods Q1 and some other good Q2, so we had our old budget constraint before where M is our budget or income, which was equal to P1 times Q1 plus P2 over Q2, but with P1 equals 0, we have a budget constraint that only looks like this. M equals P2 Q2. That, of course, if you work that through, and we'll see that a little later on as well, how you do that, this creates problems, okay? Another example occurs when we have non-market goods or services. There's no market for determining what the price would be, so we let Z be a good that's not traded in the market, but still has value. All right, so think of it. Grizzly bears are really not traded in the marketplace, but still they have value. All right, we as a society want to keep grizzly bears because they have value to us, just simply knowing that they exist and that they're part of the wild. So let Z0 be the amount of some non-market good that's initially available, and a person would prefer to be at Z1, a higher level of the good in question, because it'll provide more utility. But since there's no market, more cannot be purchased. So you can't go out and purchase grizzly bears and leave them out in the wild. So consider this. So we have a good that's not traded in the marketplace, Z, and we have all other goods represented up here. So this is like, this would be like a Q1, and this would then be the Q2 up here. And our budget constraint is simply this horizontal line at M, where M is the amount of prices times goods that we have. So it's very clear that if we're at Z0 and we're offered the opportunity to go to Z1, we'd like to do so because it results in a higher indifference curve. All right, we end up on a higher level of indifference, and that's what we would like. We have more utility units. So when the constraint is qualified, as when M equals P2 Q2, rather than M equals P1 Q1 plus P2 Q2, so in other words, this P1 has a price of 0, then the first derivative of X is equal to 0, and it's very easy to show that the second derivative, the first derivative of the objective function with respect to that same variable X is 0 as well. So in other words, the partial of the constraint with respect to X1 is equal to 0 because of the P1 being 0, while then the objective function, the first derivative of the objective function with respect to X1 is 0 as well. All right, let's return then to tangency. So you'll notice here that we have two nonlinear functions, f of x, where we just use this little v to indicate that there's some value at that particular level of the objective function. And of course, we're going to have more indifference curves, if you like, coming out of this as well. For example, there's an indifference curve here, which would give you a higher value of v. And there's one here, which would give you a lower value of v. And notice the cool little thing about this particular package I'm using is that when you draw a line and you hold your pencil or pen at the end of it, when you're finished, it'll automatically smooth that line for you. But the point here is that this is a higher level of v, and this is a lower level than this value given over here. Now, the constraint set looks like this, and it's got a it is bowed in a different direction. So the curve g of x is also nonlinear, and it has to be convex, while the function f of x, the objective, has to be concave. And right here is where our x star is, and there's a common tangency between those. So we can look at the common tangency, and we note that it's given by the slope dx2 over dx1. All right, and we'll look at that a little bit further. So along this curve g of x, all right, c is common. So if it's your budget constraint, well, which would be generally linear but not always, we find that this curve here would have the same amount of income being spent. All right, and along this curve we have that any change in g of x has to be 0. So that brings us back all the way to this function up here. All right, so along the curve, this one here, okay, pardon me, not that one, this one here, okay, along the curve g of x, the change has to be 0, so that, in other words, c remains, so that we continue to spend this amount of money on it. Okay, so let's go back to our diagram there, and we find that dg of x is 0. The slope of g of x at any point, again, is given by d of x2 over dx1. So the change in x2 as we change x1, and then that's equal to the negative of the first derivative of the constraint with respect to x1, and divided that by the second, the first derivative of the constraint with respect to the second variable x2. And likewise, the slope of x1 of the objective function at any point is given by this dx2 over dx1, and it's given by the negative of f1 divided by f2, the ratio f1 over f2. At the tangency point, then, we get that the change in, or the slope of the line has to be equal in terms of the slope of g and the slope of f have to be equal to each other and equal to the slope of this common tangent here. All right, and in that case we get this equality where the negative of g1 over g2 is equal to the negative of f1 over f2. The negatives fall out, and we get this tangency condition right here. This is the same result we'd found in the previous lecture, and as we will discuss later, the objective function has to be concave, while the constraint has to be convex. Now, we've looked at linear constraints, but those are basically quasi-convex, and as long as f of x is concave or quasi-concave, and g of x is convex or at least quasi-convex, we can be pretty well assured that the optimum is a maximum. But in order to guarantee that, we really have to look at the difference between necessary and sufficient conditions. So we have to look at second order conditions. The tangency condition that we have here, all right, so what we would do is we would find the values of x star using this condition. That's what we call a first order necessary condition. So the tangency condition is considered to be a first order necessary condition, but given that, generally there are many solutions that can satisfy the constraint g of x equals c, but few, and hopefully only one, that satisfies the constraint and the tangency condition. okay? Now that's where the problem occurs. You may have more than one solution satisfying both the constraint and the tangency condition. And if we do find multiple solutions satisfying the constraint and tangency conditions, the first order solution in other words, we need to determine which of those is somehow the best. So the problem is the first order conditions are the same for finding the maximum of the objective function as they are for finding the minimum of the objective function. But it's important to recall that maximizing the value of the objective function is the same as minimizing the value of the negative of the objective function. And we will use this notion here, we will use later on when we're talking about programming. So in this case, both the max of f of x and the min of negative of f of x satisfy the constraint and tangency conditions. Now the easiest way to find out if you've got a maximum or a minimum is by perturbing the system, or in other words, moving away from the optimal x star. So choosing, so suppose you have x1 star and x2 star. What you do is you move away from those slightly. So you take a value slightly to the left or to the right, a value higher and a value lower than the ones you have, and you resolve the objective function for those values, and you compare that to the values if you only have x star. All right, and if the value that you get, if suppose you're maximizing, suppose that you've maximized, you found out what the value of the objective function f of x star is, and then you choose some value of x that's slightly different from x star, and we're talking about not just by x star, I'm talking about both x1 star and x2 star, and you calculate the value of the objective function for a point just a little ways away from that objective function. And if you find that the value at that point is higher than the value of fx star, then you've got a minimum. If you find it's lower, then you've got a maximum. So one of the best and fastest ways of checking whether or not you've got a minimum or a maximum, whether or not the second order sufficient conditions are satisfied, is simply to pick a point on either side of the solution that you have, or maybe check both sides and determine whether or not the objective function is higher at those points or lower. And if it's higher, then you've got a minimum. If it's lower, you're guaranteed you've got a maximum. So how does one determine if one has a max or min? Via the second order conditions. Well, if you're given that f of x star, you got to test. So given f of x star, you just test some points on either side of them, and dx here is a small deviation from x star. And if you find that this value here is greater than the one you've got before, then x star is a minimum. If it's less than, then the solution is a maximum. So further exploration of the data may need to be done in order to determine if you actually have a global maximum or minimum. And you can think of it as a bit of a wave function. Some points are going to be higher, some lower, and what happens is you, through this arbitrage condition and the constraint condition, you find all of those turning points. Some are going to be minimums, some maximums, some will be higher than, some maximums will be higher than other maximums, and in order to find those, you have to do some further exploration, or, as we will see in a later lecture, a more complicated mechanism for determining whether or not you have a max or min, whether or not the second order sufficient conditions as well as the first order necessary conditions are satisfied. But we'll leave that for a little later on. Thank you for watching this video. There are many more videos in this 2 to 3 course series. A list of videos, the order in which they should be taken,
and links to them are found under mathematical economics at the website indicated below.